Okay, so we will discuss the tutorial for previous week on nonlinear equations. Yeah. So the first question is, suppose you have a function f is a combination of linear and exponential like this. So there is no formula to find the zero of this function, right? So then we will try to find the function by, try to approximate the function by polynomial, right? And after that, we find the zero of the polynomial, and the zero of the polynomial will approximate the zero of the original f. So how do we do it? So we do step by step. Yeah. So the first step is to construct the interpolation polynomials that interpolate at 3 points. So we do it by maybe by computer divided difference table. So let me share my piece of paper. Oh no, sorry, not this one. Yeah. So I haven't. So have you? So maybe you haven't seen my piece of paper yet. So let me try to adjust it in the correct position. And okay, so now let me share the screen now. Okay, so you can see it, right? So now, so remember the question is, you have a function f is x minus 9 to the minus x, yeah? And you try to interpolate at x1 equals 0, x2 equal 0.5, and x3 equal 1. So what are the value of those of f at those points? So you can see that f of x1 is just f of 0, right? So it's just 0 minus 9 to the 0 is just minus 1. Okay. And then f of x2 is 1/2 minus 9 to the minus 1/2. So just 1/2 minus 1/3. So just minus, just 1/6, yeah. Then fx3 is just 1 minus 9 to the minus 1. So 1 minus 1/9. So it's just 8/9. Okay. And so now you make a divided difference table. So if you remember Newton form, so you have to make a divided difference table. So this is x, so 0, 1/2, and 1, and the y is minus 1, 1/6, 8/9. And then you compute this entry. So this entries will be 1/6 minus 1 become plus 1 divided by 1/2 minus 0, just 1/2. So then this one just give you 7/6 over 1/2. So divide by 1/2 multiplied by 2. So 14/6, what is 7/3? Okay. And so the second one will be a over 9 minus 1 over 6 divided by 1 minus 1/2. So, okay. So common denominator is 18. So I got 18 here. And so I got 16 minus, so multiply by 3, so minus 3, yeah, divided by 1/2. So become 13 over 16, so 13 over 18 and multiply by 2, so 13 over 9. Okay. And then after that, you just compute the last entry. So the last entry will be 13 over 9 minus 7 over 3 divided by 1 minus 0. So, okay. So if you do it correctly, then this one will be, so 13 over 9 minus 14 over 9 will be, is it 13? 13 over 9, yes. No, sorry. So this one should be 21, yeah. So 21, yeah. Is 7 over 3 is 21 over 9, yeah. So minus 8 over 9. Okay. So this one gives you minus 8 over 9. Yeah? So now if you remember the way to construct the Newton form, right? You have to take out the divided difference coefficient. Yeah, so those are the coefficient, and then you write down what is P. So you write out P will be minus 1 plus 7 over 3 x minus 0 plus or minus 8 over 9 x minus 0 x minus 1/2, right? Okay. So this is a quadratic, and you can solve the quadratic to get out the 0. So if I write down correctly, so this one will be minus 1 plus 7 over 3x minus 8 over 9x squared plus, so 8 over 2, which is 4 over 9x, yeah, and minus 1. So you got so you got 7 is like 21 over 9, so 25 over 9x minus 8 over 9x squared. Okay, so this one is just a quadratic, and you can solve for the quadratics, yeah. So if you remember question, so there's a question, yeah. So for interpolation, do we use Newton? It's up to you. You can use Lagrange polynomials, but you will get the same, answer. Okay, so if you use Newton method, divided difference, then you get out this polynomial. And if you use Lagrangian, then you get out some polynomials, but when you expand it, it will be the same. Okay, so I leave it for you to check. I mean, you have to make sure that your calculation is correct. Yeah. Okay. So then in this case, I just put in, like calculator to find the 0 here. So I just leave it to you to find the 0 of this one. So x will be, well, I mean, you have to choose which one is in the correct interval. Yeah. So the plus and minus, and 25 over 9 square minus 4 A over 9 and take, well, so this one is the delta, right? So this, well, this one is maybe the delta first, yeah. So this is the delta, yeah. So b squared minus 4ac, and then you have x is plus or minus, no, maybe minus 25 over 9 plus or minus square root delta divided by 2a, so 18, so 19, no, 16 over 9. So you can plug it in calculators and you find out what is the correct answer of x, okay? And so this one, the 0 of p will be the approximation of the 0 of the function f, which is non-linear. Okay, so this is one way to find the 0 of the function without using Newton method and fixed point iteration and so on and so forth. Yeah, but just by interpolation. So we go back to the next question. So so you use this polynomial to find approximation. Okay, so we solve already, yeah. So to get out the 0, so you can get the 0. So now the next question is solved by bisection method, by fixed point iteration, by Newton's method, by secant method. So this one, like, you do it by hand, okay? So I just leave it to you because I think this one, either you do it by hand or you write a simple MATLAB script to compute the iteration, yeah? So now we move to the next question, which is more difficult, yeah? So the question 3 is about Newton method, but so this one is the case when you have f prime p equals 0 and p is a solution of the function. So remember Newton method, you have f prime p here, right? And when x go to p, then if f prime p equals 0, this blows up, okay? So the Newton method will be in trouble. So you will see that in this problem, we will prove that in this case, we don't have a quadratic conversion of Newton method anymore. So you just have a linear conversion, okay? And then if you modify the Newton method by multiply 2 in the second term, then you can recover quadratic conversion. Okay, so now we do it step by step, yeah. So suppose I make the function g to be x minus f of x over f prime. So show that limit of gx when x go to p equal p, yeah. So now we do step by step. So this is question 3. So now, so we have g of x is x minus f of x over f prime. Okay, so x different from p, and we want to show that the limit of gx when x go to p equal p. Okay, so how do we do that? So, well, first we plug it in first, yeah. So limit of g of x go to p, we just limit of x go to p, yeah. And you see, I mean, you can split the limit into two limits. So limit is linear, so you can split into this. Okay. So the first term is okay because there's no singularity, because when x go to p, then this one is just equal p, right? How about the second one? The second one, when x go to p, you have fp, what is equal 0? F prime p equals 0. So you have 0 over 0. So you have an indefinite form. So how do you solve it? How do you fix it? So how do I fix? Yeah, so you just use L'Hospital rules, yeah. So differentiate top and bottom. So what is the name? It's just L'Hospital rules, yeah. So now if I use L'Hospital rules, then this one become limit of f prime x over f double prime x go to p. So in this case, f prime p is equal 0, right? But f double prime p is non-zero. So remember the assumption is f double prime p is non-zero. So this one is okay. So 0 over something non-zero just equals 0. So this one gives you 0. So p minus 0 is just equal p, yeah. So everything is okay, yeah. Okay, so now the second question is, now if I so this is the first part, yeah. Now the second part, so for the second part, I need to write down, yeah. So the second part is, now if I define the errors En is Pn minus P, okay, then I need to show that the limit of En plus 1 over En when n go to infinity is 1/2. So there is no more quadratic conversion, okay. So now how do we do that? So remember, what is Pn plus 1? So Pn plus 1, okay, is Pn minus f prime Pn, sorry, Pn minus f of Pn over f prime Pn. Okay. So this is the formula for Newton method. So if you take Pn plus 1 minus P, then you got Pn minus P minus f Pn f prime Pn, yeah. So this one just En plus 1 equal En, okay, minus f Pn over f prime Pn. Okay, so the error is the relation between En plus 1 and En is like this. Yeah, but now if you take a limit, I mean, if you take the limit, this one just 0 and 0 and then 0 over 0, right? Because Pn go to P, right? So Fp equals 0, f prime Pn equals 0. So you have an indefinite form here. Okay. So how do we do it? So this one is, if I write down a little bit, so this one will equal rather the common denominator is just f prime Pn, right? And this one just En f prime Pn minus Fpn. Okay. So still 0 over 0. So essentially, you cannot use L'Hopital rule here, right? Because you take derivative is still zero over zero, yeah. So now the trick is we're going to use Taylor expansion. Okay, so hopefully if we use Taylor expansion, we can somehow transform this one to something non-singular. Okay, so that is the plan, yeah. So suppose I label this one is my equation number 1. So this one is equation number 1, yeah. So we save it here, yeah. So now we go back to the Taylor expansion. So now Taylor expansion of function f around Pn. Okay. So now I will expand f around Pn. Around Pn, yeah. So if you remember, Taylor expansion will be f of x equal f of Pn, okay, plus f prime Pn x minus Pn, yeah, plus f double prime Pn over 2 x minus Pn square plus something of higher order. So I just put it x minus Pn cubed. Okay, so this is a big O notation. It's not zero. Okay, big O notation. It's just umbrella. So umbrella that say that okay, the next term will be of order x minus Pn to the cube. Yeah. And now what happened if I put x equal p? So I put x equal p. So what's so special about p? So I got f of p, right? Equal f of Pn. So I set, yeah. Plus f prime Pn, p minus Pn. Okay. Plus, sorry, only f prime, yeah. F double prime Pn over 2, p minus Pn square, plus big O notation of p minus Pn cubed. So what's so special about p? So what is p? So what does it equal to? What does fp equal to? You forgot the equation already. You forgot the, okay, equals 0. Yeah. So remember p is the 0, right? So fp equals 0. Yeah. And remember what is p minus Pn? So what is p minus Pn? En, well, actually minus En, yeah, because this is minus En, yeah. So now this is minus En squared. So now I write it a bit more, yeah. So I write 0 equal f of Pn minus f prime Pn En, yeah, plus f double prime Pn over 2 En square, right? Plus something of higher order. So I just put a big O here. Okay. And if you remember what we wrote before, so now I show you the equation 1. Yeah. So you compare equation. So you see equation 1 here. So the equation 1, yeah. So it should be to maybe I show you like so this is equation 1, yeah. Okay. So you got En F prime Bn minus Fp. And here you have Fp, sorry, Fpn minus EnF prime. Okay. And remember there's a 0 here. Yeah. So they are related. Yeah. So this one, it just means that minus Fpn plus F prime Pn En can be written as a higher order term. Okay. Yeah. Okay. So now if I put this one, so now suppose I put this one is equation number 2. Yeah. Then I put 2 into 1. So put 2 into 1. So put 2 into 1. Then remember what this is my 1. Yeah. So 1. So the very left is just En plus 1. So now I have En plus 1 is just equal F double prime Pn over 2 En square plus O En cubed over F prime Pn. Okay. So because you interested in the quotient En plus 1 over En, right? So if you divide it by En, so you got En plus 1 over En is F double prime Pn over 2 En plus OEn square over F prime Pn. Okay. But if you look at this, so this one, maybe I put this one is number 3, yeah. So if you look at number 3, I cannot take the limit yet because En, when n go to infinity, still go to 0. And Pn, when n go to infinity, go to P. So F prime P is 0. So you still have 0 over 0. Yeah. So what is the next step we should do? So far we haven't used the fact that F prime P equals 0. Yeah. So how do we use it? So right now we cannot take the limit, yeah, because we still have I just lost the connection, so sorry about that. So now we go back to number 3, yeah. So we look at it, and we still have 0 over 0, right? But we haven't used the fact that F prime P equals 0, right? So remember we used the definition of the Newton iteration, yeah. We use the fp equals 0, right? To derive the bottom, the top part here. And now what should we do to get rid of the singularity in the bottom part? So remember, we haven't used the fact that f prime p equals 0. So any suggestion? Any suggestion what to do? So remember, we haven't used the fact that f prime p equals 0, right? So now, if you look at the way I use the Taylor expansion, so maybe going back a little bit, yeah. So this is a bit tricky, yeah. But now, if you, yes, you are very, very close, yeah. So we have to somehow use the Taylor expansion, but for the derivative, yeah. So yeah, one way is you differentiate the Taylor expansion, yeah. But essentially, the same thing is like you use Taylor expansion for f prime, but not for f, yeah. So it's the same, yeah. But that is the correct way of thinking it. So now if I use Taylor expansion for f prime, yeah. So now I do exactly the same. So Taylor expansion for f prime around Pn, which is essentially just a differentiate of the Taylor expansion for f, yeah. So you got f prime x equal f prime Pn plus f double prime. Okay, so now the prime become a double prime, yeah. Pn x minus Pn, okay, and now become the third derivative. Remember, because you differentiate, yeah, x minus Pn square, yeah, and plus higher order. And we do it again exactly like before. So we set x equal p. Okay, then you got f prime p, yeah, equals 0, yeah. And you know, here you have f prime Pn plus f double prime Pn minus En, yeah. So maybe minus here, okay, and plus f triple prime Pn over 2 f prime Pn is f double prime Pn En minus f triple prime Pn over 2 En square plus or En cubed. Okay. And now, so remember number 3. So this one is my, say this one is my number 4, right? And now I put number 4 into number 3. So what is number 3? Remember my number 3? Well, you can try to use Lobster rules. Let's see whether you can solve it. I mean, you can try to use Lobster rules, but the problem is, you know, we have Pn and we have En. So I mean, if you can get it works using Lobster rules, it would be great. But at least I know one way to do it by Taylor expansion. Okay. So now if I put back into my number 3, yeah, I put f prime here, yeah. So then what do I have? So then I replace f prime by f double prime en, f double prime en square, yeah. So I replace, so I put 4 into 3. Then I will have, so I just assume that you have copied it down, so I just copy it down here as well. So you have f double prime pn 1/2 en plus OEN square. So this one is from the previous formula number 3. And now you put in the new stuff here. So the bottom part, the f prime pn become f double prime pn en minus f triple prime pn over 2 en square plus OEN cubed. Okay. And you see we can cancel en. At least we can cancel en on the top and the bottom. So you got 1/2 f double prime pn plus OEN divided by f double prime pn. So en got cancelled the top and the bottom. So triple prime pn over 2 pn plus OEN square. Okay. So now what is the limit when n go to infinity? Look at the very last equations. So what is the limit? And when n goes to infinity? 1/2, yeah. Because en go to 0, right? En go to 0, en square go to 0. So p double prime p is non-zero. So you don't have a singularity anymore. So the ideas of this exercise is somehow you need to express f prime at a higher order. And then when you take the limit, then because the higher order terms, you know, like doesn't go to 0. So that's why you can take the limits, yeah. So the question is whether you can use lobster rules. I've tried, but I couldn't get it. So if you can get it, so please let me know, okay? Anyway, so this is number 3. So new script, yeah. Well, let me share you this MATLAB screen. Okay, so suppose I take the function f to be, so I clear everything first, yeah. So suppose I take my function f to be logarithm x. So remember, logarithm x here is just a natural log multiplied by x minus 1. Okay. So sorry. So in this case, then p just equal 1, right? Yeah. Because if you put x equal 1, you got logarithm 1 equals 0 and 1 minus 1 is just equal 0. And what is the derivative? So derivative is, so df will be, okay, so logarithm of x, when you take the derivative, it's just 1 over x times x minus 1 plus, so logarithm x again. So this is just a product rules, yeah. And you can see that so for f1, it equals 0. But when you put df1, it's also equals 0, right? So you can try to take the second derivative, and you will see that second derivative is non-zero. Okay, so I just leave it for you to do it. But now I want to show you the Newton method. So remember, we start with, say, 1.5. Okay, and I will make like 15 iteration. Okay, so Pn will be Pn minus f of Pn over df of Pn. Okay, remember this is the formula for, so I reuse Pn, yeah. So remember this is the formula. So Pn plus 1 is Pn minus f Pn over df of Pn, yeah. So now what is the errors? So remember the errors, does it make sense? I mean, sorry, the errors is still make sense, yeah. But what is the error? So I want to save the errors, yeah. So the errors is Pn minus P, yeah. So P just equal 1. So En is Pn minus P. Okay. And now I want to take the ratio En over En plus 1. Okay. So if, so now I just print f. Yeah, I just want to print out okay. So well, maybe right now is n, yeah. So n is essentially is k, yeah. Maybe I should put n here instead of k. So n. So I put n equals something here, and then I put out Pn is my solution, yeah. And then I put the ratio, so En over En minus 1. Remember I mean, you can take En over En minus 1 instead of En plus 1 over En. So it's just the same, yeah. It's consecutive. So I put a floating point here. And now I put in my N. I put in my Pn, yeah. Then I put in the error. So now the errors now should not be k anymore. Should be at n, yeah. So En over En n minus 1. Okay, but this one doesn't make sense if n equal 1, right? Because En n minus 1 minus 1 is just equals 0. So this one you have to say that if n is bigger than 1, then you print out the ratio. Otherwise, don't do it because it's not defined. Okay, so now I run it. So I run it. So say test question 3, week 8. So you see that if you look at my output, you see after 15 iteration, you see the limit here. So start from 0.47 and it get close to 0.499997. So it close to, so when you take n and go to infinity, it will go to 1/2. You see, so you don't have a quadratic conversion anymore, right? But you have a linear conversion. Yeah. So that is what happening. Yeah. So and you prove it already. So we prove why is the case. Okay. So you prove it by theory and you check it numerically by the program. Okay. So now maybe we should move to the next question about so where's the problem? Okay, so you can use the same trick. Okay, I leave it to you to prove this formula. So if you modify the Newton method by multiply by number 2 here, then you recover the quadratic conversion. Okay, and you use the same tricks, just Newton method for 2 equations. So if you, so let me copy down the equation, or maybe I can, but you see the problem already, right? So let me share my piece of paper and I copy down. So now the equation is, so you have 2 equations, yeah? So x squared minus 2x minus y plus 0.5, which is equal 0, and x squared plus 4y squared minus 4 equals 0. So this one is of the form f xy equals 0. Or maybe I write down here. So it's of the form f xy equals 0 and g xy equals 0. Okay. And now what is a Jacobian? So the Jacobian is just partial f with respect to, so it's a matrix, yeah? So partial f with respect to the first variable, partial f with respect to the second variable, partial g with respect to first variable, partial g with respect to the Now the next question is, how do you find, so given first iteration, how do you find the second iteration? So x1 y1 is given, yeah? So in this case, it's just equal to 0.25, yeah? And how do you find x2 y2? So if you remember, you know, the Newton method for one variable is just x. Well, maybe I should not use x, maybe use z, yeah, z, because we have x and y already. So the Newton method for one variable look like this: f of zn over f prime at zn, yeah. But now if you have 2 variables, then divided by f prime doesn't make any sense. Okay. So the f prime will be replaced by the Jacobian. But when you divide it by f prime, it just means that you multiply by the inverse of the Jacobian. So if you have a vector, say v, yeah, vn plus 1, then this one is just vn minus, you know, the Jacobian inverse, yeah, time f at vn. So f now is a multivariate function, yeah, capital F, yeah. So this is the formula for the multivariate Newton method. So you replace divided by f prime by multiply by inverse of the Jacobian, yeah. So now in our case, what is the vector v? So the vector now just x2 y2, right? So it's a 2-dimensional vector. Is vn is just x1 y1. Remember, you start from there. x1, y1. Okay. And now we have to compute each element, but x1 is given, y1 is given. Okay, so x1 is given here, y1 is given. So what is f of x1, y1? So what is f of x1, y1? Well, it's just 2 square minus 2 multiplied by 2 minus 0.25 plus 0.5. So 4 minus 4, 0.5 minus 0.25. So it's just 0.25. Okay. And so what is g of x1, y1? Well, so g will be your 2 square plus 4 times 1 over 16. Okay, so minus 4. So 2 times 2 is 4, yeah. 4 minus 2 here, minus 1 here. So this one is 4. This one is 8 divided by 4, just 2, yeah. Inverse, yeah. So do not forget the inverse. 0.25, 0.25. So the inverse. So how do you compute the inverse? So now if you read the question, yeah, then the inverse has been given. So if you go back to the question, you will see that the inverse of this matrix is given already. So you see, so A is 2 minus 1, 4, 2. So it's the matrix, the Jacobian matrix. And the vector B is 0.25, 0.25. So A backslash B just means that A inverse times B. So then give you this solution already. So you just put it in. Okay, so you don't have to compute the inverse. Okay, so that is the question 2, right? So if you put it in, then you get something like this, yeah. So plug it in calculator, so we don't have to spend time to do this, yeah. Okay, so the next question is, so one more question, yeah. So now if you go back to this question, then now we have another system, okay? So x squared plus y squared minus 2 equals 0 and xy equal 1. And you can verify that the solution are 1, 1 and minus 1, minus 1. You just plug it in directly. So 1 plus 1 minus 2 equals 0. So 1 times 1 equals 0. So now the question is, what difficulties might arise if she tries to use Newton method? Well, so what is the Jacobian for this one? So the Jacobian for this one, if you write down, okay, so let me do it quickly, yeah. So if you write down the Jacobian quickly for this system, then the Jacobian is just, in this case, it's just 2x, 2y, and then differential versus x is y, and this one is x, yeah. So now, if you put in 1, 1, so if you put in x equal 1, y equal 1, then you see that the matrix will be 2, 2, 1, 1. Okay. So what is this matrix? Well, what is the determinant of this matrix? So question, answer, yeah. Yeah, so the determinant is 0. And remember, you need to inverse the Jacobian, right? And the determinant equals 0, then it's not invertible. Okay, so if you apply Newton method, yeah, because remember 1, 1 is the solution. So when it close to the solution, the matrix is singular, it's not invertible. Close up. So exactly like derivative equals 0, right? So in this case, it's a two-dimensional, so the matrix becomes singular. Okay, then you say that, okay, the difficulties is when you know, close to the 0 of the system, then the Jacobian become singular matrix, and you might not be able to solve it. Okay, and the last question is about the navigation equation. So if you look at the lecture notes, you will see that the equation is very straightforward. So this one is like related to the GPS example at the beginning of the chapter. Yeah. So you just write down and then you write out the Jacobian. So any question? So we have only 1 minute left. So I stop the recording now.